In the history of physics, one mathematical prediction stands out for being wrong by a margin containing 120 zeros. It is the single most inaccurate calculation ever made in the name of science. Physicists reached this number while trying to calculate the vacuum energy of the universe. They were attempting to determine exactly how much energy exists in the empty space between atoms. That error isn't an isolated mistake. It mirrors the biggest unexplained gaps in modern astronomy: the discovery of dark energy and the conflicting expansion rates known as the Hubble tension. These three crises point toward a shared conclusion. The vacuum error, the expansion tension, and the mystery of the dark sector are all symptoms of the single flaw in our foundational equations. The standard model assumes the vacuum of space is a continuous, three-dimensional bulk fluid. To find its energy, we take every microscopic vibration and add them up, filling that volume. But if the universe encodes its macroscopic limits on 2D surface areas, this bulk fluid model leads to a massive dimensional mismatch. Physics has corrected this mismatch before. The Aronnax-Bohm effect demonstrated that macroscopic observables can depend entirely on global topology rather than local bulk fields. Correcting the dark sector requires treating expansion as a geometric constraint at a boundary rather than a mysterious energy density filling a volume. We can find the rules for these boundaries by looking at the surface of a star, where gravity and radiation are forced into equilibrium. Every star has a radiative decoupling layer. It is the exact surface where the outward pressure of light finally escapes the inward pull of the star's gravity. When we balance outward luminosity with inward surface gravity at this boundary, the specific mass of the star disappears from the equation. It cancels out completely. What remains is a pure geometric invariant, pi cubed over 15, or approximately 2.0671. This constant dictates gravity at a boundary regardless of the system's size. Independent measurements of the Sun and nearly 200 other binary stars show their parameters cluster tightly around this exact value. Because this boundary rule is scale invariant, it can be projected from a single star to the limit of the observable universe, the cosmic horizon. This mirrors the area scaling laws of black hole thermodynamics. Stephen Hawking and Jacob Bekenstein established that a region's information capacity is fixed by its surface area, not its volume. To project that 2D surface constant into a 3D volume, we apply a geometric scaling rule. A sphere's volume is exactly 1/3 of its radius times its surface area. This requires dividing our boundary constant by 3. Dividing pi cubed over 15 by 3 defines the dark energy fraction as exactly 0.689. In a flat universe, this leaves a matter fraction of exactly 0.311. These derived fractions align with the empirical data gathered by the Planck satellite. This solves the 10 to the 120 vacuum catastrophe. The excess energy never existed. It was a mathematical artifact caused by treating two-dimensional boundary information as a three-dimensional fluid. Beyond composition, this boundary rule dictates the universe's evolutionary timeline, specifically the moment expansion shifted from slowing down to speeding up. Acceleration begins the moment the diluting matter in the universe is overpowered by the constant negative pressure exerted by the geometric boundary. Using our geometric fractions, the equations plot the onset of cosmic acceleration at a redshift of exactly 0.642. The Hubble tension, the mismatch in expansion rates, also resolves when we consider how we measure distance. If we model the space between galaxies as a discrete lattice of packed spheres rather than a smooth fluid, geometry introduces a kissing number of 12. Measuring across this lattice creates a structural defect fraction of 1/12, which bridges the gap between our two expansion measurements. These cosmological milestones are the predictable results of the pi cubed over 15 boundary geometry. This geometric framework also dictates the ultimate asymptotic future of the universe as cosmic expansion continues toward infinity. This stable geometry excludes the Big Rip, a scenario where phantom energy accelerates until it shreds galaxies and atoms apart. Because dark energy is a fixed geometric projection of a surface, it cannot become volatile or phantom. It lacks the physical properties required to tear space apart. As matter dilutes to zero, The expansion rate of the universe asymptotically approaches a stable, eternal limit of exactly 60.6 kilometers per second per megaparsec. The universe operates as a self-contained geometric system, with its past, present, and eternal expansion written into the stable ratios of its own boundaries.